Hi. Thank you. Hi, everyone. So it's my second time at Hackfest. I was here 6 years ago, and it become bigger and bigger and bigger. And it's really great to be there. So why I'm here, I'm going to speak about Windows system and code signing protection, typically authenticode for people that know this topic. So who am I? I work for Sekoia. I work for the incident response team, and I basically focus on Windows internal and malware analysis. I'm French, as you can hear, but I live in Luxembourg and I work in Luxembourg. So, what is authenticode? I think more or less everybody in the room already heard about this. I think is the signature mechanism developed by Microsoft. So when you have a signed binary, in fact, the technology behind the control of the signature, etc., is the authenticode. So on this presentation, I will speak about two. Yeah, I need to scream. Yeah. It should be a little better. Yeah, it's okay for you? Better? Yes? Yeah. Okay. So the presentation will be divided in two parts. On one part, I will speak about the kernel implication of authenticode. And on the second part, I will speak about the userland application of authenticode and binary signatures. Basically, I'm going to speak about how malware play with this protection, how they bypass it, etc. And on all the example I will provide, it's real example on real life. Everything is on the wide, except some small tricks I will give to you, and I think they will be on the wide soon. So binary signature is when you try to execute the binary, this kind of image where you have the verified publisher. Sekoia, in this case, is our own certificate. And if it's not signed by a trusted editor, you have this yellow windows and it's right, publisher unknown in this case. So I'm not going to speak about this thing, but I will go deeper. So what is the implication for the kernel? Basically, since Windows 7, 64 bits, so yeah, if you're not used to speak about Windows security mechanism, on the same version of Windows, if you don't have the same architecture, sometimes you don't have the protection enabled by default. It's the case on Windows driver signatures. If you're in 32 bits, it's not enabled by default. It's only enabled on 64-bit version of Windows 7. So on this specific architecture, you cannot load driver on your system if it's not signed by a legitimate company. So basically, it could be a synonym to end of rootkit, end of malware that work in kernel space. Obviously not. We have a rootkit today, even if you have this kind of protection. So I'm gonna explain to you how malware developers bypass this protection and how they are able to load unsigned driver in the kernel. So from my point of view, you have two approaches. The low-cost approach, not really technically good, and a really, really interesting approach. On the low-cost approach, it's simply on Windows system, if you are kernel developers and you are developing your own driver, you need to be able to disable, you need to have the possibility to disable this protection. Because imagine you are writing your driver and you compile it, you want to test it, extra. You do that 10 times per day. And you don't want to sign your temporary binary each time on each you had a printf and you don't want to compile it and sign it, etc. So you have the capability to disable the signatures control on the kernel. To do that, you have bcd-edit.exe command, and you can switch your system in test mode. When you do that, you need to reboot first, and at this time you are able to load every driver on your system, but you have this kind of message in the bottom right on your system. You cannot remove this text. So on your infrastructure, if you have machine with this kind of text, you probably have a problem, or it's a developer machine. So something interesting is this message is displayed by winlogon.exe. So once you enter your username and password on Windows system, winlogon.exe will show you your desktop more or less. And it's this process that will show you this specific message. So something I already saw on Wild is malware that are injected in winlogon.exe and simply invert the condition. So if the system is in test mode, the message will never appear. It's simply on memory patching. So it works. The system is really in testing mode, but you are not able to see the message on the desktop. But if you use bcd to check the current state of your machine, it's in signing mode, test mode, sorry. For me, it's the low-cost approach. It's not really technically interesting. It simply hides the message. I worked a few times ago on a really good example of rootkit bypass, and it's Uroburos malware. Uroburos, Turla, Snake, whatever the name, each AV company have its own name. How the developers bypass the kernel protection in this case? In fact, they use a legitimate driver. In this case, it's the driver of VirtualBox, and they use a vulnerability on this driver, legitimate one, to disable the kernel driver signatures. How it works? So it's a really old vulnerability, 2008. And on this vulnerability, on vbox-drv.sys, you have the capability to switch one specific kernel memory address to 0. You cannot do more than simply switching one address to 0. How it works internally on the kernel, the driver protection? It uses a global flag called g_ci enabled. It's CI is for code integrity. Each time you will see CI something, it's code integrity. And when the code integrity is enabled on your system, the flag is at 1. When you disable it by bcd-edit command, for example, it switches global flag to 0. I think you can guess how they use the vulnerability. In fact, they load the legitimate driver, use the vulnerability to switch the 1 to 0, and at this time, the code signing is disabled on the kernel. When you do that, and when you use bcd-edit.exe to check the signatures mechanism, you will see it's disabled. Because how works bcd-edit.exe? It checks this global flag. So you switch the global flag. By consequence, bcd-edit say you are in test mode. So it's, if, for example, you are able to use bcd-edit on all your infrastructure, you are able to check if you have machine in test mode or not, even if this trick is used. Here, you've got a complete implementation of these techniques. You can simply check the code, and basically you can resume everything in one line. You open the symlink vbox-drv, you specify the address where you have your CI enable flag, and it will switch to 0. So it was, for me, the first time I saw a real bypass based on kernel vulnerability and not simply by a trick of hiding message. So it was quite interesting. Few months after this case, I saw a new case where I was able to identify how the rootkit was loaded on system. And in this time, it's more or less the same approach. The developers use a vulnerable driver. In this case, it was a novel driver, and use this vulnerability to disable the code signatures. So the main difference between Uroburos and Derusbi is the implementation. In this case, the implementation is more clever. Let's check. The vulnerability is not simply switch specific address to 0. In this case, it's really code execution in kernel space. So how to analyze this kind of thing? I use my debugger WinDBG. I make some breakpoint when the device NICM was accessed. NICM is the device, the symlink created by novel driver. In this case, I got the data sent to the symlink, and this data is in fact a shellcode directly sent to the kernel. If you disassemble this shellcode, you can see it's really, really small. For shellcode, if you are used to play with shellcode, generally it's longer than 5 instructions. So, what is this shellcode? The first thing is, in fact, it doesn't really do a lot of things. He performs a OR 8 on a specific address inside of your kernel. If you look who is the owner of this address on WinDBG here, you can see it's ci.dll. So ci.dll code integrity. So when I saw this thing for the first time, I knew that the malware is making an OR on the kernel address. I don't know what is this specific address. I simply know it's owned by ci.dll. So I check the value inside of my debugger, and before the exploitation, my value was 6. After exploitation, it's E. 6 or 8 is E. So what is this value, and why the attackers perform this modification? It's really, really specific, so it means something. Not for me, but for the attacker, it means something. So thanks to a post from Joru, I was able to quickly understand why he's modifying this specific thing. If you look at the source code available on this blog post, you've got the URL here, you can see how works internally the beginning of the CI functions. At the beginning, you can see that a variable is set to 4 or 2, so it's 6. Something to you, the 6 was the value before the execution of the shellcode. It does several stuff, blah, blah, blah. And if I'm in test signing, so test mode, CI option, so my 6 or 8, it's exactly what the shellcode is performing. If I look on ci.dll, I can, so on the right, I got a specific address that finished by E30. And on my shellcode, it's finished by E30. So the shellcode, in fact, simply modify an internal variable of ci.dll to disable the code integrity on the kernel. So it's really clever, because in this case, it doesn't modify a global flag. It doesn't disable globally the code integrity check on kernel, but they modify an internal variable inside of ci.dll in order to disable code signatures. And what is really interesting with this approach is that bcdedit.exe checks the global flag. And on this case, the attackers never modified the global flag. So we disable the code signing without modifying the global flag. So bcdedit, in this case, say to you, you are not in testing mode. But in fact, you are. So it's pretty interesting. Another well-known team, Equation Group, used, I think, the same techniques to load their driver. I don't have the sample, sadly, but I've got the Kaspersky report, and they mention that to bypass modern OS security mechanism, etc., kernel mode, exploit legitimate driver, include one of the Cloud CD programs. This driver contains a vulnerability, blah, blah, blah. So it sounds a little bit like the two other cases. you have a CVE, you have the .sys legitimate one with a vulnerability, and the problem for me is on the Kaspersky papers, it didn't provide the hash of the sample. So I'm not able to find and to check and to analyze or confirm the analysis of Kaspersky. So I asked to Kaspersky if they can share the sample with me. And I'm lucky because they say, yes, we can. But because the life is never really easy, I asked in March, they say yes. And I asked to April, they say yes. And in May, in June, in July, and I'm still waiting. So they are okay to share the sample with me, but I'm waiting since March. So I don't have them, and I'm not able to analyze exactly how they bypass the kernel signature mechanism. Another case I analyzed a few weeks ago is IDRV. It's a rootkit developed by APT22 fancy bar sednit guys. In this case, the problem, I only have the .sys file, the malware, the rootkit, and I don't have the stage before that disable signature extra. So I'm not able to see how they bypass this protection. But they bypass it because it's a malware in 64-bit architecture. So they must disable the signatures. So if someone in the room has this dropper or the hash of this dropper, feel free to contact me. And if you say yes, give it to me. Or next time I add a new slide with your name and each boss. So yesterday I published a blog post about the analysis of this rootkit. So I don't really speak about the authenticode protection, but it's really nice if you want to understand how analyze rootkit, because it's really simple. In this case, the developers forget to remove comments. It's really easy, no obfuscation, extra. So it's a really a really good use case to analyze the first rootkit. So, and my paper is write like a tutorial. So I think it's more or less easy. So on each case I analyze, the malware use the same approach. They use a legitimate driver and exploit a vulnerability on it to disable authenticode. Generally, people say to me, yes, but you are speaking about old exploit from 2008 and stuff like that. And what about the expiration date of this legitimate driver? The thing is, it's not supported on the kernel. You can perfectly load expired binary signed by an expired certificate. It's not a problem. In kernel space, it's not supported. I think it's not supported for production reasons. Because if tomorrow they enable this thing, if you don't update your software, everything will shut down, simply. So I think it's a reason. I don't exactly know why, but in this case, you have a driver expired in, I cannot read in fact, 2013. It's a VirtualBox driver, but you can load it perfectly on Windows 10. It's not a problem. Another question people asked me on previous session is, yes, but we have a revocation list of my certificate. Yes, but visibly it doesn't work on kernel 2. It's not documented or it doesn't work. I don't really know. I don't find documentation about kernel revocation list. I only find documentation about userland revocation list. So maybe you have a revocation list, but it's not documented and I didn't find it. Yeah. And to be honest, generally people doesn't really care about revocation list, and company have problem to update systems, so don't speak about revocation list. I will give you an extra trick to load an illegitimate driver if you need one day. I don't know if you remember this leak. Duo.com company published a leak about, I don't remember which manufacturer, maybe Dell or Lenovo, I don't remember. On the image of your system, they include private certificate. And the company published a paper, and the press speak about this paper a lot and say, you can make man in the middle, and you have private certificate, you will be able to generate traffic, and it will be traced by computer, etc. etc. Everybody spoke about the man in the middle threat, but in fact, from my point of view, something is at least maybe more interesting. They provide certificate of the Bluetooth driver. So you have the private certificate of this for Bluetooth driver. And thankfully, this certificate expired a few years ago. Thankfully, it's not supported by kernel. So you can perfectly take this leaked certificate, sign your driver, and load it on Windows 10 system. It works. And some people say to me, yes, but why AV company doesn't blacklist this leaked certificate? Because if they blacklist it, you cannot use your Bluetooth device anymore. So of course they didn't blacklist this certificate. And it works really well. Yeah, it's exactly what I said. So, and what's the future concerning kernel signatures? So we are waiting for the future since a lot of time. Microsoft would like to force only Microsoft signed binary inside of the kernel. So what does it mean? If you are developers, you create your driver and you send it to Microsoft, and they make some check test, I don't know, and they sign it for you. And you provide to your customers a signed certificate by Microsoft. So at every Windows update, they said, next time we will do that. Today, it's not the case. We check on Redstone 2 Windows 10 update from this few months ago in August, I think, and it's not implemented for the moment. Yeah. So first part concerning kernel space, it's over. You have more or less all the tricks publicly available, all the tricks I worked on concerning this specific bypass. But since few times, we have new implication on userland application. So the first implication is protected process. So what is a protected process? Is something available since Windows 8, and you have a really, really good documentation from UNESCO concerning this topic. How it works? In fact, you have specific binary on your system, only Microsoft binary. Microsoft is the only one to be able to create a protected process. And in fact, it's linked to authenticode and binary signatures. If you look on this binary, you can see you have protected process like verification flag. So it means if you try to execute this process, csrss.exe, it will run as a protected process. What is a protected process? It's a process that is protected. No, I'm kidding. It's a process that you cannot read remotely the memory. In Windows, you don't have a protection between memory reading. If you are administrator, you can read every memory of every process. It's like that. In this case, it doesn't work anymore. If you are administrator and you want to open in memory CRSS.exe, it's not possible to open it in full access. You cannot remotely read the memory of the process. They implemented the query limited information. You are able to open it and have some information, but not the full memory. So it's something interesting from security point of view. If you look at, for example, I'm thinking about point of sale malware, how they work. They basically open the process, read the memory, and looking for a track 2 in memory. But it's only available for Microsoft, sadly. Something new for linked to authenticode on userland is protection against binary injection. So it's between bracket cut, so it's Microsoft definition. So they published a blog post on Windows when the threshold 2 update of Windows was available with We have a new feature on Windows Microsoft Edge, the new browser of Microsoft. We have a new feature, and attackers are not able to load unauthorized DLLs inside of Edge. So great. I wrote a blog post about how it's implemented, and I had a really fun exchange with UNESCO about what is documented and not documented. On my blog post, I said it's undocumented, and Alex said to me, "Why do you say that? It's on the winentity.h in the SDK of Microsoft. So if you think that the .h file is documentation, it's documented. If you think it's not documentation, it's not documented. Question of point of view. How does it work? Today, on modern Windows 10, you have a new structure inside of your process that defines if it's have mitigation or not. And one of the mitigation is I think is process signature policy. And yes, I think is this one. And this structure define if your process is able to load unsigned DLL or load only Microsoft signed DLL or load only DLL from the store. Basically, Microsoft signed, store signed, etc. So you have a new system inside of Edge that allow Edge.exe to load only DLL signed by Microsoft. So typically, how works toolbars in the past? You have a DLL on your system, and Internet Explorer loads this DLL, and what is the purpose of this DLL is to show the new toolbar. Microsoft had a new protection that block this kind of unwanted load. You are not able to load unsigned or even signed but not by Microsoft library inside of Edge. How it works more in detail, when you perform a load library, when Edge performed load library, it has to the kernel to create a section and blah blah blah. And at the end, you have the CI.dll library that checks the signature of the DLL. And if the DLL is signed by Microsoft, he says, okay, you can load it on the kernel on Edge. If it's not signed by Microsoft, the memory allocation is forbidden and it will not be loaded. Is it bulletproof? A lot of people ask me, yes, but does it work? Does it really work? In fact, it's a little bit hard to answer this question. From a toolbar point of view and this kind of developers, yes, it's efficient. It works. You cannot load, or I didn't find a way to load unlegitimate DLL inside of Edge. But you can always make some dirty injection by loading a shellcode, for example. When you load a shellcode, you allocate remotely memory, you put your shellcode in memory, and you execute it. And you don't really use load library. You don't need to use load library. So in this case, it doesn't work. You can continue to allocate memory, put your shellcode, execute it, it works perfectly. I read several times the blog post of Microsoft here, and they really, really well choose each word, and they didn't lie. They perfectly describe this yes and no, in fact. So yeah, I push on my GitHub a small tool. It's an injector, really simple, but you have two flags. One flag where you say, I want to inject a DLL, and you put in argument a DLL, and it will use the load library function to load it. And you have a second argument where you can directly send a shellcode. And thanks to the script, you can easily make some tests to check it works, it doesn't work, etc., etc. So it's pretty useful. I finish for each part. No, you can ask me question or make a awkward silence. It's nice for me too. Or upload to wake up your neighbor. And I will be there for today. So if you don't want to ask question in front of this crowd, you can simply pick me on the outside. It's perfect for me too. Thanks.